My name is Grace O'Malley. I'm Vice President of Technical Operations within iNEMI, and I'm also the project manager assigned to this project, which is the module with separable single mode expanded beam optical interface for edge coupled PIC optics. Today we're going to present a webinar, a call for participation webinar. So we now have a project plan in place, and we are looking to engage other participants in the project, and that's the focus of today's call. The majority of the webinar will be presented by the project chair, Peter O'Brien, who's head of the group of photonics packaging at the Tyndall Institute based in Cork in Ireland. Before we jump into the project itself, I will just give a brief overview of iNEMI and our collaborative project model that we use, so everyone gets an understanding of where we're coming from on that. And then I'll hand over to Peter to discuss the project. As I mentioned, you're welcome to submit any questions through the chat. And we'll also unmute the lines at the end of the call to address any questions also. Okay, so iNEMI is a consortium. We're actually around now for about 27 years, and it's a global consortium composed of, leading stakeholders in the electronics manufacturing supply chain. So it includes everyone from material and equipment suppliers to the OEMs and EMSs, and as well as some of the leading research centers involved in electronics manufacturing related research, and some government agencies as well, such as NIST in the US. We're involved in understanding the future trends, particularly in terms of technology requirements for electronics manufacturing, and then we develop a collaborative, pre-competitive collaborative projects that help address the needs and infrastructure gaps that have been identified through our road mapping processes. And today's project is a good example of that. Just to give you an idea, we're right now in what we call our launch phase for this particular project. So there's been some ongoing work here in the early stages of defining what the project will be and putting together a project plan. That was open for general industry input. We had a team of approximately, I think, 10 organizations actively involved here. It's been approved by the technical leadership within iNEMI, the technical committee, and now we're going through this launch and sign up phase so that we can get enough critical participation to move forward. Our projects, as I mentioned, are pre-competitive and collaborative, but they do have some common denominators across them. They typically address, a common need in the industry, and that's best addressed collaboratively. As I mentioned, we have good representation from across the global supply chain, so that I think gives us typically good momentum and engagement on the projects. And, they are always aligned ultimately with the members and the industry's commercial needs. The type of deliverables that come out of our projects can vary significantly. In some cases, it may be a software tool, such as this life cycle assessment tool here. It could be data in terms of characterization of the warpage of new and advanced organic packaging technologies. It may be new test methods here in terms of a creep corrosion test method, and recommendations to the standards bodies. So as Peter will talk about, the deliverable coming out of this particular project is actually a demonstrator module. So we're going to physically build and test a module to evaluate I suppose, the capabilities and the assembly capabilities for the optical modules here in this particular project. Being involved in this project, enables the participants to contribute to the development of this demonstrator. It allows you to operate, collectively, so resources can be leveraged across the team. And, we operate our projects under an agreement, either as a member or as what we'll call a fast turn member, so that, we're covered under intellectual property, our intellectual property policy as well. The team, those involved in the team, obviously will get access directly to the data and information coming out of the demonstrator. The team plan to promote this and publish it externally, but obviously what will be published will be decided on by the team members themselves. As I mentioned, we have an umbrella structure which enables organizations to work together pre-competitively. And so there's a document, a couple of documents that need to be reviewed before organizations sign up to being involved. But one thing I wanted to highlight here is typically many of you will know our projects are only available to existing iNEMI members. We do on occasion, though, nominate some projects that we consider to be strategic, where we want to engage non-members, and also can be done in a reasonably short time. This project we hope to complete by the end of this year, so in an 8 to 9 month time frame. And because of that and the strategic nature, this has been nominated by the technical committee as a fast turn project. So that enables non-iNEMI members to participate in this one project for a one-off fee, and also under the auspices of an MOU, which addresses the intellectual property policy and the requirements of operating on an iNEMI project. So I just wanted to make you aware of that, and I'll talk a little bit more in detail at the end of the call today. So with that, I'm going to hand over to Peter, who's going to give you an overview on the project and discuss what our plans are for going forward.
Okay, Grace, can you hear me okay?
Yeah, hear you fine, thank you.
Yeah, I'm getting a reflection. I don't know whether maybe you want to go on mute. That's better now. That's better. Perfect. Okay. So hello, everybody. I think some of you have already been involved in this discussion, and really what we're doing today is to open it up to others. There's a call here to kind of build a wider team. And we had a call earlier today, Grace and myself, with some people in Asia, because obviously we want this to be a global activity as much as possible. And just to mention who's been involved so far, so ourselves at Tyndall in Ireland, we also have Molex, US Connects, MRSI, the packaging equipment company, Senko, Embryonics are an Irish company involved in packaging, Tom Brown in Rochester, the Fraunhofer team in Berlin, 3M in Minnesota, and Intel and Hyperscale. And I suppose from what you can see here, there's technological people, research, academic, including ourselves, connector companies, equipment companies, and end users. And really, I suppose the message is that no matter where you fall within that kind of grouping, we're keen that we build up the number of partners. So be if you're involved in design, research, the application, the equipment, or whatever, we're very keen to involve as many people as possible. And ultimately, as Grace said, in this first project, the goal is it's a short-term project, relatively short-term project. It's to make a prototype. So it's to demonstrate the principle of this pluggable connector. So Grace, if you just move on to the next slide, please. Yeah, so just the background to the project. So some of you may be aware there's the IPSR roadmap, and essentially that's like the semiconductor technology roadmap, but for photonics. And I was involved with some of the people I've just previously mentioned in the last few graphs around and developing kind of a packaging roadmap. And one of the things that came out of that was the need for a pluggable connector. So in a sense, what we're, some of you may be familiar with the bonded fiber array. So with a silicon photonic device, you can bond, for example, with epoxies, directly bond the fiber array to the chip. And that's got its benefits, but there are applications, and there is a growing interest in being able to have a pluggable connector where you can basically detach the fiber, the ribbon fiber, for example, from the device. And that involves using an expanded beam, a collimated expanded beam using micro-optics. So essentially we're looking at the micro-optics, and I'll show a view graph in a second around micro-optics with the photonic chip and micro-optics on the connector side. And that, as I said, there's been the roadmap. We also have done an industry survey. So in 2019, we did an industry survey across, just packaging fiber optic connectors, and really what came out of there, a dominant kind of demand or an interest was around this pluggable edge coupling connector. So here we're talking about edge coupling. It's not grating couplers, it's edge couplers, edge coupled silicon photonic devices. And again, ultimately where we want to go with this, it has to meet certain criteria around being reflow compatible, optimized coupling losses. But in this first phase, we do not want to achieve, we don't want to make the best type of pluggable connector. We want to demonstrate the principle. So that involves, using what's available right now, so the materials that are already available. And phase 2 will go into, assuming we demonstrate that proof of principle. Phase 2 next year will optimize the designs. So there's a demand and there's a lot of background to the project. It wasn't just decided, anecdotal evidence. There was a roadmap and there was a survey, quite an extensive survey. So Grace, if you just go to the next. As I say, this first phase really is around developing the principle, showing the principle, and a physical demonstrator. So from that, we need devices. These are the silicon photonic chips, the micro optics, and the connector. So there's a design activity, there's a packaging activity, and there's a test activity. And as I say, at the end of the year, the plan is to demonstrate that principle. Phase 2 then will optimize the design. So this year, we're not planning on making a big investment in developing new micro optics. We're basically using what we have, and obviously making a good choice to get as good a coupling efficiency as possible, but it's not optimized. And I think that's really important, because that second phase, we want to reduce the risk. We want to know that the principle of this type of pluggable connector works. So that's really kind of the focus of phase 1. Okay, Grace, next. Okay, so this is an older design, and I have another design in the next view graph. But essentially, if you just look at some of the key elements here, but the main one to look at is the edge coupled PIC. So what you can see here is you can see a silicon photonic chip, and it has micro lenses at the edge, and then we have the pluggable single mode fiber. And essentially, what you have here is the blue ribbon fiber. It's in a ferrule with micro lenses, and you can imagine the light is coming from the ribbon fiber. It's collimated with the micro lenses, and on the receiving side, if you will, on the PIC chip, we have almost a reciprocal design, pretty much, with micro optics bonded onto the edge of the PIC and refocusing back into the waveguides of the silicon photonic device. And in essence, what you're doing is you're able to, with that expanded beam, you've got a fairly relaxed alignment tolerance between the pluggable connector and the PIC chip. So that makes it amenable to mechanical design, plus or minus up to 10, 15 microns. Actually, that's what the numbers are telling us. So essentially, you're not bonding the ribbon fiber, that blue ribbon fiber, directly to the PIC anymore, and it's making it pluggable. So if you go to the next view graph, please, Grace. So again, this is an image taken from Molex, and Tom Maripod has been working a lot with us on this, defining this work. So essentially what you see here is you see a silicon photonic device, edge coupled, and one of the critical parameters is the mode size. So at this point, we're using 3 micron mode size edge couplers. We're getting our hands on 10 microns soon, so that means we'll be able to work with a different type of micro lens. So with a 3 micron mode size, we're using silicon micro lenses. So SUS Micro Optics are providing us with those silicon micro lenses, and this first phase we're using a 3 micron edge coupler. So you can see the micro lenses are aligned to the edge. We have an expanded beam, typically within the range. As the gap. That gap is defined typically by the width of the beam. So for a 50 micron beam, you're talking around a millimeter gap. For a 100 micron beam, it can go out to about, say, 2 to 3 millimeters. And we're talking about a dB loss, plus or minus, about that kind of number, about a dB loss in the coupling. And on the receiving side, as I said earlier, you've got the ribbon fiber in an assembly with micro optics. And again, you can see the empty connector that Molex said they'd be able to provide in this particular demonstration phase with the pin connectors. So it's basically using these alignment pins in a mechanical housing. So that's where the mechanical design comes in. The PIC chip is going to be in a mechanical housing with a receptacle for these pins. And essentially, as I say, with the expanded beam of 50 to 100 microns, you can have a relaxed alignment tolerance up to plus or minus, say, 10 to 15 microns for about a dB loss. And that means then the mechanical machining of the package and the components, the mechanical alignment components, it's all very doable. So as I say, the end of the year is to demonstrate the principle, demonstrate the proof of principle of this technology. So if you go to the next view graph, so really the scope of this project is to work on the design, and it's the optical and mechanical design. It's to do the packaging and the assembly and the testing. And we're looking for participants to support and even, just to look and advise in this project. So as you can see, we're looking for participants to support across the design, the packaging. It's more packaging than fabrication. Essentially, we're taking chips and micro optics that are already available. So there's not very much fabrication. We're not going redesigning a PIC for this or redesigning micro optics. That will probably come in phase 2. So if you go to the next view graph, please, Grace. So just about the timeline. So this is a kind of a fairly high level overview. So when we sit down at our next kickoff meeting, the plan is to really kind of like flesh out the details here. But as you can see, the plan is that by the end of the year, we'd make a proof of principle demonstrator. So starting off with looking at the resources. So basically what we're doing there is checking, do we have the chips? Do we have the micro optics? Do we have the connector? What's needed in the mechanical assembly, etc. Then work on the design, getting all those materials into place, working on the packaging and the assembly, and then the testing. So essentially the testing is just going to be looking at the repeatability of the coupling loss with that pluggable connector. Then the next phase, as I said, phase 2, is more optimization, and that's going to require a longer time frame. So as you can imagine, fabricating new micro optics based on optimized design for expanded beam, looking at an optimized pluggable connector, etc. That's going to take some time to design and manufacture those parts. So we predict an approximate time frame of about 18 to 24 months, as opposed to say 8 to 9 months for this first demonstration phase. The next view graph, please. So I won't go into too much detail here, but essentially what we've been doing, the group to kind of define the project, and this is a very nice approach that iNEMI take, I think, with all their projects, is what is the project and what is it not? So I won't go through all the points, but essentially what we're saying is it's a project to demonstrate the proof of principle. It's not to maximize coupling efficiencies. It's not to optimize the manufacturing process. It's not to make a solder reflow compatible design. We want to prove the principle, and in phase 2 we'll address many of those finer points. Okay, so the next view graph, please. So as I said, we've been looking recently about the resources that are required. So on the right hand column here you see the chips. These are the silicon photonic devices. So we have devices, for example, we've got devices we're using from our photonics packaging pilot line that they were fabricated in IMEC, and the 3 micron mode size adapters. We have micro lens arrays with the connectors. Obviously then we need some of the design and modeling capabilities. Looking at the materials, the assembly materials, that's essentially like the epoxies. So we have a number of epoxies, but you might be a partner who could contribute interesting and novel epoxies that we might want to use in that process. And ultimately, maybe in phase 2, we'll really do a more detailed investigation of those to optimize the process. And then finally, testing. So, at this point, testing is really to prove the principle, look at the repeatability of the coupling loss, but somebody on the call might have an idea of a more elaborate, maybe, but not too long kind of test phase, an additional test that might be valuable. And if we can squeeze it in, we would definitely consider it. Okay, next view graph, please. So what are the benefits of participation? So as I said, we're really trying to make a global activity here. I think one of the big challenges we face in integrated photonics today is there's a lot of still fragmentation. So people are going off independently, developing processes which can be difficult to scale. So really what we're trying to do here is make a kind of a critical mass and disseminate that information widely. So I suppose one of the key benefits, you'll see how these complex packages are designed. You see all the different stack up, the mechanical and optical stack up. Look at the photonic chips. So you might be a connector company, but interested in the silicon photonic devices themselves and the micro optics, the packaging equipment and the materials that are used to package those. So there's multiple ways when you look at it, there's from different stakeholders, there's different benefits can accrue from the project. And again, one of the big objectives here is because the long-term objective is, well, hopefully the medium term, is we push towards development of some kind of standard. And that's very important. Now, the focus here is again around data centers, but there are other markets which will find this technology of benefit too. So it's really, you know, there's the potential for in other markets like for biosensing, this type of pluggable connector is also of great interest too. So there's other benefits, not just within the application domain we're talking about today. So Grace, the next view graph. Oh yeah, it's questions and answers. So that's a very short summary, and we're open to questions. Thanks.
Great, thanks very much, Peter. If anyone has any questions, please feel free to unmute yourself, and you can ask those directly, or you can submit them on the chat. I don't think we have any so far on chat, but if anyone would like to unmute and address any questions to Peter or myself, you're more than welcome.
It's all perfectly clear. We had a few questions this morning, and people were asking, I suppose I answered the question, one of the questions was around the gap, so that distance between the connector. And again, just very briefly, my colleague Camille on the line has done a lot of work in Tyndall on this. So the beam waist, really, the beam diameter really does affect that. So with a smaller beam diameter, the gap is smaller, but the angular alignment tolerances are more relaxed. So there's this trade-off. So the optical design will look at this and understand those different types of parameters. So that was a question that was asked earlier today. I think one of the general questions people tend to ask is around the scope. And as I say, hopefully I made that fairly clear. We're not trying to kind of do too much in this early phase. And really what we're doing is use the materials that are available. I should also mention that there was work done previously. Terry Smith, for example, led a previous project on fiber to fiber connectors. So in a sense, one part of this, you know, silicon photonic and fiber pluggable connector has already been, a lot of work has been done on that. So this kind of phase 0, if you want to call it. So there has been work done, and this is really picking it up and moving it forward to bring the photonic device into the mix.
Great, thanks, Peter.
So as I want to point, again, like as I say, we're really interested in getting more partners involved and promoting this as I wouldn't say a firm standard, but we want to move towards that direction. And it's not just hardware like devices or consumables that we need. We're also interested in end users who might see a need for a particular design aspect, or it could be a material supplier that might have you know, an interest in certain types of reliability. So it could be reliability testing, but you know, we don't want to focus too much on that. But from a testing perspective, you know, you might have a view on it and maybe taking the Demonstrator and looking at certain critical reliability features that maybe can help us define phase 2 a little bit more in more detail.
Peter, this is Terry. I think one of the things we've talked about a lot and that people might appreciate hearing a quick summary of would be your concept of how the alignment technology for the lens that's going to go in on the PIC, how that alignment technology is expected to evolve through the program. So initially, will it be totally robotic type alignment, etc.?
Very good point, actually. So that's a good point. So one of the big challenges with edge coupling and with micro optics is it's quite a challenge to align the micro lens to the edge of the chip. And one of the main reasons is that it's very difficult to see the waveguides. They're small, and there's not much topology. There's not much structure there to see, and the camera on the machine has there's a challenge with that. So one of the ways you get around that is you put the chip in a package, you connect it up to a laser. For example, a silicon doesn't have an intrinsic light source, so it has to be packaged and coupled with a laser, or the laser's connected externally. And that means that the package has to be pre-assembled. It can be quite slow, and that's a problem. So that kind of active alignment, if you will. One of the approaches we've developed at Tyndall, and it's a design rule we're implementing kind of within the foundries, is we have a new design where we're putting grating couplers alongside the edge waveguides, and the grating couplers are connected to external edge waveguides, and it might be difficult to visualize, but the packaging machine illuminates the waveguides, the grating couplers. And you do not need to couple very much light into those grating couplers, and automatically the camera can see the edge coupling camera can see those illuminated waveguides. We call them marker waveguides. And then what you get is what we call first light. The machine then can pick up those two outer waveguides, and it can very quickly align to those. And because the pitch is consistent across all the waveguides, all the optical functional waveguides in between those two outer marker waveguides are self-aligned to the microlens array. So, you know, that's a new technology, and we would like to think we would bring that in phase 2, and it's going to be driving this more automated, we call it semi-active, it's kind of active-passive, but the benefit is you do not need to package the silicon photonic chip in a package and connect up a laser. It can be done on the bare device, and it can even be done when the device is flip-chipped, because the light source is transparent in silicon. So I hope that answers your question, Terry. It might be difficult to visualize everything I've said, but we're moving towards much more robotic automation. And an expected cycle time of that process will be down around 20 to 30 seconds.
Great, that helps a lot. Thank you.
Thanks, Terry. Anyone else would like to ask a question or make a comment?
Hi, Peter. This is Ari Feldman from NIST. So I can definitely appreciate the desire to move towards standardized optics. I applaud the effort here. My question is about characterization of the losses and distortion. You know, I see a gendered connector to go, you know, from a pluggable fiber connector to a silicon PIC. Is there, I mean, for the characterization aspect, is there a genderless connector that, you know, you could connect, you know, fiber to fiber and then, you know, characterize the losses in just the connectors themselves? Or is there a way to do that on the silicon PIC?
Yeah, that's a good point, and maybe Tom, you can help me out here. You know, you have a lot of expertise in that. But essentially, I don't know if I'm going to answer the question in the correct way, but we're not putting any alignment structures on the PIC that will fix the pins on the connector side, if I'm explaining myself correctly to you. So essentially, you know, and this is actually where the design and optical and mechanical design really comes into play here, and it's something we haven't really you know, developed up thoroughly yet. We've had some early stage discussions, but the alignment sequence and the assembly sequence. So as we see it, we're aligning the micro lens to the silicon independently, as I've just explained previously, and that kind of sub-assembly of micro lens and PIC will be placed on a carrier. The carrier is in a small cradle and that mechanical cradle, let's call it a cradle, will have the alignment pin kind of receptors in there. And the alignment of that sub-assembly, the PIC with the micro lens to that cradle, is very, very important. But again, because the beam is expanded, it's an expanded beam, we're working within plus or minus, say, 10 to 15 microns. So alignment features, mechanical alignment features should be possible. You know, we're talking about a plus or minus 10, 15 for a 1 dB loss. Those mechanical kind of structuring should be possible to achieve.
Okay.
Terry, I don't know if you want, it's not Terry, but Tom, I don't know if you want to add to that.
Is that Tom Brown or?
No, sorry, Tom Maripode.
I don't think he's on, actually.
Oh, is he not? Okay, yeah. Apologies. So I don't know if I answered your question, and I don't know, Terry, if you want to add to that, you have some expertise on the fiber side as well, the connectors.
I was, my interpretation of Ari's question was more around the calibration and measurement techniques for loss. Is that a correct interpretation, Ari?
Yeah. What kind of measurement and characterization are you going to employ to ensure the attenuation or distortion or losses in the connectors?
Okay, okay. Yeah, so so we will probably, yeah, that's a good question, and we don't have a thorough answer for that. So yeah, it will be connector to connector, and then comparing connector to connector to PIC, and the PICs will have a loop back. So we will know effectively know the loss in the PIC. We will identify the loss in the PIC to microlens, and then essentially kind of subtract and identify, break out the different loss contributions that way.
Okay, great. Thank you.
Great. Daniel, do you have a question? Peter? Daniel Kuchka.
I do. Hi, Peter. This is Dan Kukta. Are you envisioning this project like all the fiber types would be identical, like all standard single mode fiber, or are you planning on a mixture maybe of having some PM fiber types? And could you say more about that?
Well, I think we're kind of limited. I suppose at the moment, the discussions we've had, Tom Maripode from Molex has said Molex can provide a particular fiber connector type. Whether there's PM or non-PM fiber, we haven't considered that yet. It really depends on what they can provide. So I'm speaking on Tyndall's side, we're providing the micro-optics and the PICs, and we're looking for others besides Molex. So again, there's this trade-off between what we can achieve in this short time frame and what our partners are willing to provide in terms of materials.
And then just another question, in your figure on page 13, I think, or 11, you only show like 6 micro lenses, but can you talk about what the application needs and how much you can scale that? Can you go to 60? Or is there
very good point? Yeah, very good point. And actually, from where there's a number of challenges here. What we're beginning to see is, and again, Tom, from the connector side, there are limits on what you can mold. So a molded micro optic on the right hand side. But from our experience, where we're starting to see issues, if you have a pure PIC, just a pure isolated PIC, it can be very flat, it can be planar. But if it's bonded onto a carrier, you start to get the PIC, it'll warp. So that kind of warpage is an issue. So there are limits. I suppose in this phase, we're not particularly, it's not that we're not interested, but we're not looking at that. We're demonstrating the principle. But you're right. And I gave a talk 2 weeks ago at the OIDA workshop on co-packaging. And we've measured warpage of PICs, typical warpage across a PIC edge of 5 millimeters. We're seeing up to about, say, 3 to 5 micron when it's flip chipped onto a carrier, onto a PCB, for example. So you could imagine you have to be very careful. So if you have a very large array on the PIC side, that warpage can be a problem, and you can get misalignment across the PIC edge with the micro optics. That can cause beam steering. So there's a whole array of problems which we're not addressing in this first phase, but they do exist. I'm pretty sure they're there waiting to bite us when we start to look at them.
Dan, this is Terry. In the earlier survey that we did to try to determine people's interest in different features that would be possible for the target. The concept of polarization maintaining fiber versus standard fiber was one of the hot items. And the issue comes down to, if you use conventional fiber, then you simplify the fiber parts. But if you use PM fiber, you simplify the silicon PIC part. And the general feeling was that we should try to take the more challenging approach of polarization independent PICs with standard fiber in order to enable real high volume deployment of the fiber part of the interconnect. But like I say, there was a lot of interest on both sides of that position.
I see. Thanks, Terry, and nice to hear from you again.
Yeah, good to hear you.
Great, thank you. I think we have 2 more questions at the moment, so I'll call on Anuradha. Hopefully I'm Anuradha.
Yes.
Hopefully I'm pronouncing that
Thank you,
correctly.
Grace. This is, yeah, thank you. This is Anu Agarwal from MIT. Hi, Peter. Hi, Terry.
Hi, Anu.
Yeah, hi. I have a question about the design and modeling that you talked about. It looks as if the design is already determined. What parts of the design are you looking for that are still up and in the open?
Well, yes. Well, so we've got a kind of baseline design, but for example, we haven't modeled the connector. So Tom Maripode has proposed Molex will provide a connector. So we know, for example, certain parameters. If the beam waist is 50, beam diameter is 50, you get this working distance. So between the two micro lenses, but we don't have all the details yet of, we haven't got confirmation of that connector. So we don't know all the details around the micro lens details for that connector. So therefore the modeling hasn't been optimized with the materials. So for example, someone on the call today might say, well, I got a better connector and here's the optical parameters for that. So we'd have to model that. So as I say, we kind of know the approach we take. We know the basic principles of the model, but we haven't refined it in that regard.
Great. Thank you so much for the clarification.
And just to go back to Dan's question about the number, we see, that is a big question, especially around things like warpage and reliability. And it could be we might end up with a unit cell. It could be 4 or 8, and any more than that, you can imagine a very large array, and if the chip is warping, that could be a problem. So we might end up with kind of unit cell micro lens arrays. So we've got individual, if it's bending, you basically segment it, the micro lens. So these things might come out later on. So there's a lot of unknowns. And I think the danger is that we try and do too much looking at reliability and warpage and all these other factors. And really it's just to demonstrate almost the ideal. So we simplify it. So we're looking at a nice ceramic, for example, that we'll bond the chip onto, make sure it's pretty planar, as much as we can get it. So all these things need to be considered. And then, we'll move to the real world in phase 2, look at, replacing with PCBs if it's needed, things like that, and start to see real problems that, manufacturing faces.
Great, thanks. There's a question from David Stegall. David, do you want to unmute and ask that yourself?
Sure, can you hear me?
Yeah, you're all good.
So my question has to do with the transition between phase 1 and phase 2. So in phase 1, you're identifying readily available sort of off-the-shelf componentry to do this demonstration. In phase 2, you would hope to be able to optimize performance. So let's just expect that you're going to want to see better results than what you're able to perform in phase 1. If that means that there needs to be improvements in the connector design, how much flexibility is there going to be at that stage? Are you going to revisit some fundamental components of this design at that point, or how constrained do you expect to be going into phase 2?
Okay, so there's different areas of constraint. So I think, for example, if you look at the PIC, that's going to be one constraint, and that's limited by the mode size. For example, what we're beginning to see is there's a move to standardize the mode size. So 10 microns is a standard mode size. And that's one constraint. So that's something that's becoming more fixed. I mentioned we're starting with a 3 micron mode size from these iMEC chips, but we're moving more to a 10 micron. That's something that's becoming almost like a standard. It's more compatible with single mode fibers. The micro lens that will respond to that. So we will design the micro lens to be compatible with that. And then, the connector side, I don't want to speak on behalf of the connector people, but there will be constraints around that. It probably will be the number of fibers, as Dan mentioned. That's going to be a constraint. How many channels can we squeeze in there? And then you have like the conventional, data center, the number of channels that are needed there. So, but I think a lot of the constraints will be on the PIC side. I don't know if that answers your
thanks.
question, David.
Pretty much. Thank you.
Great, thank you all very much for your questions. I don't see any more hands raised or comments. Last call. Okay, with that, I'll just give you a brief overview of how, if you'd like to get involved in the project, how you can join. But of course, you can reach out to Peter or myself to get further information if you need more to make a decision. We are now, as I said, in the launch phase, so we do have a sign-up period. We're hoping to complete that by May 22nd, after which the project would be closed. People can apply to join, but they have to be approved by the existing team members at that point. For iNEMI members, you're probably familiar with the process, but we have a public project page. You can all go to this page and you can download the SOW, which is our statement of work or project plan, and then the project statement, which is kind of the, I suppose, the agreement document that every organization signs when they're joining the project. So for existing members, they need to review both of those, sign and submit the project statement. For non-members, as I mentioned at the top of the call, you should review the SOW and PS as well, but we also have an MOU that you would sign because you're not an existing member, and that, you know, outlines, I suppose, the terms and conditions and references the relevant policies that the project operates under, and also there's a fee associated with participating in the project as a non-member. So you can reach out to me directly, and I can go back to you with more information on both the MOU and the fee. So at that, with this, I would finish for now. You can contact me on this email address. And if you want to set up a call to discuss this further, I'm happy to arrange that. And hopefully if Peter can fit it in his schedule, or indeed some of the other team members.
Absolutely, yeah.
Been involved.
More than happy to answer any questions.
Great. Thank you very much. So with that, we'll draw today's call to a close, and thank you all for both attending and also I think for the good feedback and input here. As I mentioned on our earlier call today, you know, the team and really want to promote this development and get industry engagement, because the ultimate objective is to optimize the manufacturability of these connectors and modules going forward. So the earlier engagement, the possible, you know, the more successful this will be in the long run. So thank you all, and we look forward to hearing from you in the future.
Thanks, Grace. Thank you.
Thank you. Bye.
Bye.
Bye. Bye.